think it's time to start. This is the last talk of our semester now before summer break in PALS, given by Nebojsa Mudrinski from University of Novi Sad. He will talk on supernilpotent semirings. Please, Nebojsa.
Okay, once again, hello everybody, and thank you, Peter, for the nice introduction. It is a great pleasure to give a talk at your PALS seminar in Boulder, and I hope that my talk will be very understandable. At least I tried to prepare it that way. But okay, so the title Supernilpotent semirings, it's maybe everybody of you know already about supernilpotency as the property that is defined by the commutator. And the commutator has been introduced in the previous century, in 70s, as you know, by some people from audience here, Fraser, Mackenzie, Smith, Hagemann, and Hyman as a generalization of the commutator from groups. And in the beginning of this century, Bulatov just extended the definition to commutator of any finite length. And it was further developed by many other authors among you. And this is a complicated definition, as we all know, so it needs so-called centralizing condition and terms and so on, and the commutator is simply the smallest congruence that satisfies these certain centralizing conditions, C alpha 1, alpha and 2 delta. And I am going to show the definition of the centralizing condition introduced by Bulatov in 2001. It uses polynomials and tuples, and we assume that the values of polynomials for valuations of tuples of variables of the corresponding lengths are in delta in almost all the cases, but the very last one where we change all variables by all betas. So this is the centralizing condition, and we usually call our commutators the time condition commutator. And this is somehow universal algebraic notion. And by those commutators, we can define properties such as abelian, nilpotent, solvable, and supernilpotent. And I just recall that supernilpotent means that the commutator of any RT of the full congruences is the equality relation, and abelian is just special case of this supernilpotent property for n equals 1. N nilpotent and n solvable, they are introduced by using just binary commutator, and as we iterate this binary commutator of the right-hand side argument, then we obtained the sequence. And if this sequence became 0 after finitely many iterations, then it's nilpotent property. And if we use just commutators of commutators, after finitely many steps, if it's 0 or equivalence relation, then we call such an algebra solvable. So it's easy to see that n nilpotent for n equals 1 is the same as n solvable for n equals 1, and this is the same as n supernilpotent for n equals 1, and this is just abelian. And at least this abelian, nilpotent, and solvable in groups means exactly what it means in classical group theory. And the question is, what does it mean in other algebraic structures? So we are interested in the properties defined by commutators, in the sense how are those properties connected, and what structural properties of the given algebra do they force? For the first question, just from the fundamental properties of the commutator that are true in general in every algebra, it is easy to see that abelian forces nilpotency and nilpotency forces solvability, and also abelian forces supernilpotency. But what is not clear in general, what is relation between nilpotency and supernilpotency. And till in recent years and in recent decades, let's say, it has been a lot of contribution in multiple algebras, in algebras in congruence moduli varieties, and in algebras with Taylor terms. So supernilpotency implies nilpotency, and it's not the same one as we know by the results of Moore and Moorhead, and Kearns and Sandray. It's the thing for it's the true for all finite algebras. But the question is, if we go beyond all those classes of algebras, so to algebras that are not in congruence moduli, that haven't Taylor terms and so on, what is the situation with those properties defined by the commutators? And still, we want to be somehow close to the groups, and we just look to the algebras that are somehow generalization of groups, but in other sense, let's say. And those are, for example, semi-groups and semirings. And in semi-groups, the recent result of my PhD student, Jelena Radovic, so she defended last summer, the PhD thesis. One of the results from the thesis is the characterization of supernilpotent semigroups with zero. So semigroups with zero is just a semigroup that has an element zero, and such that the result of multiplication is zero whenever the zero appear on the left or right side of the multiplication. So in such semigroups, supernilpotency and nilpotency are the same thing, and the characterization is that S to the k plus 1 equals to the zero ideal simply. Here, S to the power of n means it is the set of all products of n elements from S. So this is how we understand this condition S to the k plus 1 equals 0. Looking at this, one can ask whether we can go further to semirings, because semirings, they consist of semigroups actually, yeah? And can we obtain similar characterization for semirings? And semirings, we all know somehow definition of semiring, but in the literature it appears many different definitions of semirings, in the sense that they have neutral elements or not, and so on. And for our investigation here, we define semiring in this way, and it is somewhere called hemiring in some books and in literature. So a semiring is an algebra with two binary operations such that both are associative. The first one is also commutative, and the first one has also a neutral element 0. I denoted by just a small o here, not to mix with the congruence, the smallest congruence 0 this is equivalence relation. And this neutral element 0 is just a 0 for the second binary operation that is also associative. So the second binary operation on the domain makes simply a semigroup with 0. And of course, we have left and right distributivity law. So such as algebraic structure we call a semiring. So this will be for us semiring. And examples are, as usual, natural numbers with addition, multiplication, and 0, but also even natural numbers with addition, multiplication, and 0. And one can ask why here we haven't just neutral element for the second binary operation. And the reason is the following. Namely, if we have a neutral element for the second binary operation for this times, then one can show just using the definition of the higher commutator and the higher centralizing condition that the commutator of the full congruences of any finite length is the same full congruence. This is quite straightforward, and therefore such semirings are not interested for the question we have mentioned in previous slides. And therefore we just look for semirings without this neutral element. Yes?
Can I ask, the 0 is not absorbing?
The 0 is, yes, the 0 is absorbing. Yes.
Because, okay. Because you didn't mention it, I think.
Semigroup S times is a semigroup with 0. Okay.
Oh, with 0. Oh, I see. Okay.
Yes. This is written
okay.
here. Yeah.
Yes,
You think on this.
Okay.
Yes. And in our semirings, we have ideals. Ideals we define as usual, I mean, as in rings, practically without inverse for plus. And for example, the set of even natural numbers is an ideal for this semiring of natural numbers. Congruences are just as always equivalence relations compatible with both binary operations. And what is the case? The case is that the congruence lattice of the semiring is not isomorphic to the lattice of ideals. And this is something that makes our life, let's say, complicated. But it was the situation also here in semigroups with 0. Here in semigroups with 0, there is also no good one-to-one correspondence between congruence lattice and the lattice of ideals. And here we used race congruences. These are congruences that can be obtained from ideals, and they were good enough. And here in semirings, we also need certain congruences. And these are the following congruences. If we have an ideal in a semiring, by rho I, we denote the smallest congruence of S such that I is quoted in the congruence class of 0. I mean, it's clear that there is full congruence such that 0 class of the full congruence is the whole semiring, and ideal is contained in this whole, in this 0 class. And if there are more, so we just take intersection, and this is the congruence that we call rho I. So for any ideal I, we associate uniquely the smallest congruence rho I. What is interesting is that if we have 0 ideal, then this congruence became equality relation. And if this ideal is the whole semiring, then we obtain the full relation. And it will be somehow good enough. And of course, it would be not so nice if we would not have the following characterization of such congruences. And this is somehow folklore in semiring theory, but everybody can show this proposition easily, I mean, straightforward, checking the reflexivity, symmetry, transitivity, compatibility, and so on. So if I is an ideal of a semiring, then this relation I is characterized by this condition practically. So two elements are in the relation if and only if there exist I and j elements from I, such that A plus I equals B plus J. This open possibilities to manipulate here with these relations and with the polynomials and centralizing condition, as you will see in the sequel. Then we move to the commutators, and first we are interested in commutators of ideals. First of all, what is the product of ideals? As in rings, the product of ideals we defined not just as a product of corresponding elements, but all finite sums of such products are also elements of the products of ideals. So exactly as in ring, and this is again an ideal of the given semi-ring. For example, S to the n, so when S is a semi-ring, is again an ideal of S. And what would be the commutator ideal? So the commutator of finitely many ideals is the sum of all products of those ideals for each permutation of the set 1 to n. So we simply permute them all possible ways and find such products and then sum those products, and we again obtain an ideal. So it all can be checked by definition of ideals. So it's an easy exercise. And this is the commutator of ideals. And using simply the fact that our semi-ring has 0, then sum of the ideal with itself is again the same ideal. And then we directly from those definitions obtain that the commutator of two ideals, S to the m and S to the n, is the ideal S to the m plus n. And the commutator ideal of length k of SSS equals to the S to the k. So this is something that we will need in the sequel. And now we move to the commutators of congruences. So we have the commutators of ideals, and now we move to the commutators of congruences because we want to connect them somehow. And the first statement that we can prove is about the centralizing relation of our certain congruences determined by ideals. So if we have n ideals of our semi-ring, then the certain congruences, so I1 to rho In centralizes modulo theta, then we know that the congruence that corresponds to the commutator ideal of those ideals A1 to AN, it is a subset of theta. This is not a hard statement to prove, so just using this definition of commutator ideals and of rho, somehow we can show that the commutator ideal is a subset of the 0 class of theta simply, and this is just by definition of the centralizing condition. So it's not a proof that I think that is too much clever to show it. And I think, yeah. And as a consequence or as a corollary of this implication, we obtain that this congruence determined by the commutator ideal is not bigger than the commutator of congruences determined by all of those ideals A1 to A to IN. And now, what would be nice, and what would we really like to have? You can just expect that we would like to have the opposite inequality here also, because in that case we will have equality here. And broadly speaking, so the commutator of certain congruences, so congruences determined by ideals, can just go down to indices in that case. Yeah? And I want to ask you, what do you think? What is the situation with the opposite inequality? Is the opposite inequality true or false? Any judge? Do you hear me?
I hope it's true.
Unfortunately, it's not true. It's not always true. And counterexample is a semiring on the set of true or false, and this is just usual disjunction operation, and we add these times that is always false, so it always takes the value false. This is a semiring in our sense, and congruence lattice is simple because this is just two-element set, so we have just equality relation and the full relation, and we can calculate that the commutator of the full relation is the full relation, but the congruence determined by the commutator of the two ideals of the full semiring is just the congruence determined by false. So it's not the same already in the binary case, but it is not all so dark and so bad because it is sometimes true. And what we can show is that in binary case, we have the following situation. So actually, to get other inequality here, we want that here we can put, instead of this theta, we want to have this relation determined by commutator ideal of ideals A1 to AN. So if this centralizing property is true, then we would have the opposite inequality here. And we can prove, at least in binary case, that this is true, but under certain implications. So this is, so for any two ideals, I and J of a semiring S, rho I centralizes rho J modulo rho commutator IJ if and only if this implication is true whenever A and B in rho I, C and D in rho J. And as a consequence of this, we will have that in binary case, and then if this implication is true, if the condition is true, in binary case, we can simply move the commutator brackets in the indices practically. And this is somehow, this lemma is somehow a bit non-trivial, let's say, to prove. It's quite technical and mock proof, but I'm going to show you at least the idea of this proof. And of course, so this is if and only if, so one implication, if we have this centralizing condition, then this condition is true, is easy, just taking polynomial P of xy equals x plus y, and the definition of the centralizing condition will provide such a thing. But the opposite is more interesting. And if we assume that the condition is true, we have to show that for 4 elements from the semi-ring, such that first 2 are in the row I and the second 2 are in row J, and for a polynomial P such that P of AC and P of AD are in row commutative of I and J, then we have to prove that this A can be changed by B. And we here I am going to explain for the polynomial xy such that this polynomial is determined by the polynomial term x plus xy. And just to recall that all polynomials in semi-rings are just finite sum of monomials. So this is one polynomial. And how we are going to prove this? From this condition, A rho IB, we know that there are I and J from I such that A plus I equals B plus J. And from the condition C rho JD, we know that there are K and L in J such that C plus K equals D plus L. So this is from our characterization of certain congruencies determined by ideals. And what does it mean? This means that A plus AC and A plus AD are in relation a row determined by the commutator of I and J. And what we want now, we want to change those A's from left-hand side and right-hand side with B's. So we want to obtain B plus BC here and B plus BD. But knowing this and knowing that A and B are in row I and C and D are in row J, we know also that AC and AD are in row J, and we can change this A, we can replace this first A with B by the assumption. So this is exactly the assumption that we have. And now the job is to replace the second occurrence of A here on left-hand side and on the right-hand side. And how we obtain this? So first, we will add on both sides IC plus ID. And then we apply distributivity law and obtain A plus I times C plus ID from one side, and from other side B plus I, A plus I times D plus IC. Then we change A plus I on both sides by B plus J because it is the same thing. And as you see, if we multiply out the brackets, we obtain BC and BD as we wanted. So on the left side, we have B plus BC, and the right side, we have B plus BD. But unfortunately, we have something more on both sides that we don't want, and we want to get rid of it. And how we will get rid of it? We are going to add, we are going to add more things on both sides, JKIL, JLIK. So we add those 4 summands on both sides, those blue. And now, why do we add those summands? Is to use again equalities that we obtain from the definition of our certain congruencies, characterization of our certain congruencies, because we have now apply distributivity law here and obtain this expression. And also on the right-hand side, we apply distributivity law here and here. and obtain this expression. Now we have even more things on both sides, but they are much nicer than it was here, because those JL plus IK, those blue parts, they are somehow in relation with zero, in relation to IJ with zero, because they are sum of products of elements from I and J, and by definition of the commutative ideal, they belong there. And this means that they are in relation with zero. And but just simply by transitivity, this side is in relation to IJ with the same thing without blue part, and also the right-hand side is the relation of IJ with this right-hand side without blue part. And this is how we get rid of blue parts, actually. And now, since C plus K equals D plus L, we have the whole red parts are the same. So this is the same element here and here. Even more, we know that B plus BC and B plus BD are in row J, because C and D are in row J by compatibility. And these red elements that seems different but are the same are in row I with zero. And therefore, if we look here, so these red parts are the same, and in the corresponding relations, we can apply the assumption and replace them with zero. And then we obtain what we wanted, and this means that P of BC and P of BD are in relation rho commutator of I and J. And this is how we changed A to B. Originally, there is one more practical situation when here X is in between two variables. Let's say this is a bit more complicated than here, but we should apply the same idea once more on the other side, and that's it. So all works by induction and on the length of terms. So it's just so the main idea of the proof is here. Yes, and this condition is now complicated or not, and it is the question, what can we do with this? But we want it somehow, and this is how we come to the additively cancellative semiring. So additively cancellative semiring is the semiring such that the commutative monoid is cancellative. So operation plus is cancellative. And in those additively cancellative semirings, we know that the commutator of those congruences determined by ideals is just the congruence determined by the commutator of those ideals. So the brackets, the commutator brackets can go to indices for any two ideals. And if we apply this to full congruences, we obtain easily the calculations. So if we have these nested commutators, or we have just higher commutator of the corresponding length, is the congruence determined by the ideal S to the k plus 1. And if we make the sequence of commutators applied to commutator for the solvability, we again can prove by induction of K straightforward that this equality is true. And actually, these two we need, and we obtain just a bit of the answer for solvability. So in additively cancellative semirings, S plus times 0 is, so it is K solvable if and only if S to the 2 to the K equals 0. So it's less or more, the proof is less or more explained. The situation is a bit better in the case of nilpotency and supernilpotency. Actually, here we doesn't need additively cancellative semirings, but just our semirings because of the statement of Meyer from 2019. He proved that a commutative monoid is a supernilpotent or nilpotent, then it is cancellative. So the proof, I don't know how the author originally proved this, but I proved it by just definition of nilpotency and supernilpotency and centralizing condition applied for the certainly chosen polynomials. And then we obtained the main results of this, the main result of this talk. So for a natural number n and a semiring s plus times 0, the following are equivalent. S is n-nilpotent, S is additively cancellative, and S to the n plus 1 equals 0 ideal, and S is n supernilpotent. So nilpotency and supernilpotency also is semirings. Those semirings that we consider is the same thing. And as a difference in characterization with semigroups with 0, it's not just that S to the n plus 1 equals the 0 ideal. It's also should be additively cancellative, so the operation plus should be cancellative. And how to prove? So this is the equivalence of three statements. So one can prove such that 1 implies 2, 2 implies 3, and 3 implies 1. So first 1 implies 2. Since semiring is nilpotent, by Meyer we know that it is cancellative, and semiring is additively cancellative, and what we had already, so S to the n plus 1 equals the 0 ideal. And we proved 2. The most interesting part is 2 implies 3. And this is, again, quite technical part that needs some additional lemmas and statements. But I'm going to explain this for the case n equals 2. And for a certain polynomial, again, we have in mind that polynomials in semirings are just sum of monomials. And for n equals 2, we should prove that if s to the 3, so 2 cube, equals the 0 ideal, and if S is additively cancellative, we should prove the centralizing condition C1, 1, 1, and 0. And to prove this, we take 6 elements from S, and we are going to assume just this polynomial. And just to explain that it is a good representative is the fact that S to cube means that every product of 3 or more elements from S is practically 0. It has no impact here. And also, so those monomials that make sum should be either linear or quadratic. Constants also has no impact on everything. And here, if we put just xy, additionally, it will not have impact because of cancellativity. So, if you believe that this polynomial is quite representative, or at least it is good to catch the main idea of the proof, we know that these 3 equalities are true. So if we change x and y with a's and b's, such that we didn't put both b's here, and z once by c and on the other side by d, we assume that all three equalities are true, and we want to prove that the fourth equality, that is when both x and y are replaced by b's, so it would be b1c plus b2c equals b1d plus b2d. We want to show this knowing this. And how we will manage? We will sum the second two equalities and obtain this equality. By commutativity of plus, we have this equality. And now by the first equality on the previous slide here, so we have made plus of those two. And by the first equality, we know that underlined sums, it is the same element, and then we apply cancellativity for plus and obtain what we wanted actually, this one. And this is how, and this is simply how the proof works for this special polynomial. But as I told, it is a good representative for the general proof. And 3 implies 1. So here we assume that S plus 0 is supernilpotent, and again by Meyer it is cancellative, and therefore the semiring is additively cancellative, and we know by our calculation that this nested commutator equals to the congruence determined by S to the n plus 1. And it will be zero congruence because zero congruence is the commutator n plus 1 commutator of the full congruences, or in the other words of those row S's. And by the first statement that we had, the nice one, it is greater or equal to the congruence determined by n plus 1 commutator of ideals of S. And this is again the same thing, row to the S, row of S to the n plus 1. What? Sorry? And this is 0S, and that's it. So this is somehow the proof of the main result. As a corollary, we know that abelian is simply one supernilpotent, and we obtain that the semiring is abelian if and only if S is additively cancellative, and the multiplication is the zero multiplication. In finite case, cancellative monoid is a group, and therefore we obtain the finite semiring is abelian if and only if it is a zero ring. So ring where multiplication is always zero. And what is more interesting is that we can characterize supernilpotent and nilpotent semirings by the same property of the semigroups that are here to build this semiring. Namely, semiring is K supernilpotent or nilpotent if and only if the monoid of the first binary operation with zero is, and also the semigroup with the second binary operation with zero are K supernilpotent and K nilpotent. I just want to draw your attention that this condition here is just the condition that is obtained by definition S to the n plus 1 in the semiring sense as we defined. And this condition here in semigroups is just more simpler. It's just, okay, not to go so so much back, is just n plus 1 product of n plus 1 elements, set of such products. But this is not the same, but this condition in semigroup and in semiring sense is equivalent. I mean, it's easy to see. And this is just what is important for the proof of this corollary. So that would be, I think, the results that we obtain about the practically many properties of the semirings defined by commutators. What are the directions of the next research? So further research plans. We like this zero, and maybe we are going to check what can be done in the case of just group weights with zeros. Then the second thing would be semigroups that have no zeros but have one-side zeros, left zeros or right zeros. Then in general, what can be done if we have just algebras with zero, and especially if we have, let's say, expanded semigroups, so semigroups where we expand it by some additional operation. They can be all semigroup operations or maybe not, and semirings are simply such example of such algebraic structures. What I forgot to tell in the beginning, the results that we have presented here are obtained in the joint research with Milica Shobot. She obtained a graduate degree in Novi Sad, and after that left for master studies in Bonn in Germany. So this was all, and I thank you for your attention.